According to science, during its entire existence, a star would struggle tirelessly against the action of gravity, which tries to crush it against its own core. To overcome gravity, it would need to generate energy, which would happen through the fusion of hydrogen atoms. This fusion would result in the formation of helium atoms and the release of enough energy so that the star could continue to shine. Einstein surprised the world when he suggested that gravity would be nothing more than the accommodation of stellar masses to a curvature of space. In short, the masses of stars could directly bend the space around them. The intricacies of gravity remain a mystery, as the mechanisms that would have generated it are not known for sure. All that is known is that it exists and the way it works. In images of the universe, enormous importance is given to the role of the observer and his memory in the way he interprets physical reality. In this translation process, light and cosmic radiation are the indispensable tools that we use to define, for example, the direction of the action of the force of gravity. Let's cite some assessments of cosmological events made by scientists with the aid of light. Light allows us to assess the mass and volume of stars, gives us information about their brightness and their chemical composition. The redshift of radiation is used to assess distances in space, and, in the same way, to get a sense of the distance of stars in the direction of our past time. There are countless examples, and they attest to our total dependence on the messenger from space. Gravity is no exception to this list. To know that space is curved, the only tool available is light. The mass of the Sun, for example, would be able to deflect the light emitted by a distant star as it passes by. Problems arise when the space-time continuum is kept in mind. It would result from a virtual fusion between light and space, expressed in the way we treat both in the same way. If the light stretched to red, space would follow the movement. If it were to contract towards the blue, space would also contract. These expansion and contraction movements of space would, in fact, characterize only the behavior of light while it executes its harmonic movement. So, let's think about the concept of future light cone of an event. If Beta Andromeda went out right now, we would have no way of knowing its death in real time. This shows that space would be outside the communication process. In this case, there would be a virtual rupture of the continuum. In order to communicate the death of the star, space would depend on its messenger. This break in the continuum, which cannot be measured directly, suggests that future events do not yet exist for the observer on Earth. This is not a problem of the universe, but of those who depend on its memory, as its memory only recognizes events that would have already happened. So, if space were to bend or stretch in our future, we would be left with an unsolvable problem. Space would be deprived of the power of direct communication, and light would be transiently retained. This was due to the consequent polarization of light associated with the contraction of time during the expansion. It sounds complicated, but it's all very simple. When space stretched into the future, it would tend to concentrate the mass of a star. This, according to the theory of relativity, would be followed by the complementary contraction of time. Beyond certain levels of this contraction, movement in space could not be measured. As a result, the star's future light cone would flatten over the two dimensions of space, which are width and length. the light would be virtually retained until there was the necessary reversal in the direction of the arrow of time. The inversion would allow time to dilate and make it possible for the observer to measure relative motion in space-time. There could not be a polarization of light coexisting simultaneously with the measurability of time. That is, the cone would flatten in our future and polarize the light because it would have lost its third dimension, represented by time. This would be valid for the Doppler effect, which would be one of the applications of polarized light. The aforementioned effect, therefore, would be part of a package previously packed. The contraction of space, which we see in our past following gravity, would be a secondary movement of accommodation of stellar masses to a change in the geometry of space, whose origin is not known. As the curvature effect would coincide with the harmonic behavior of light and not of space, we could suggest that the forces involved in our universe would be conservative, as seen in the mass spring set. Both in the spring stretching phase, which, in the case of space, would have taken place inside the future light cone of a star, or in the phase of its contraction inside space-time, the forces would always point to the spring's rest state. This center is occupied by the observer. That is, the resting state would separate the two other phases, which would become mutually exclusive. If you see the spring stretching, you cannot see it simultaneously contracting. This independent action of space on light in our future attests that, in our past, gravity would not depend directly on masses. Thus, gravity could not be accused of being the cause of the implosion of a star, since it would be a secondary restoring force. Its centripetal resultant cannot be added to the other forces. It would only crush the star if space promoted the generation of inertia at an earlier time placed in our future. Inertia would depend on an increase in elastic potential energy linked to the stretching of space outside space-time. Everything indicates that there would be a state of equilibrium between the expansion and contraction phases of the universe. If potential energy were to increase unchecked, the universe would implode in on itself. If it got too small, the universe would expand forever. That would be a disaster for intelligent life.